I ask you a question about the brightest star in the night sky, and many, without thinking, will name Sirius. And if asked which star is closest to us, excluding our sun, the answer will not be long in coming: Proxima Centauri. However, there is one paradox that I cannot get out of my head. Why do we not see it? How can it be that our closest stellar neighbor, located just 4.2 light-years away, a distance negligible by cosmic standards, remains absolutely indistinguishable to the naked eye? One would think such a luminary should shine in the sky like a beacon, yet it is not there. This mystery is not simply a question of distance or optics. It is a whole story that immerses us in the very essence of how stars live and die, how planets are formed, and how inhospitable worlds can be, even those right at our doorstep. What then lies hidden in this cosmic darkness next door? And what is the main secret this invisible star holds? A secret that simultaneously beckons and warns. Let us embark on this journey together and unravel it all. Before focusing on our invisible target, let us study its stellar environment, for Proxima Centauri does not exist in isolation. It is part of the famous triple star system known as Alpha Centauri, and to comprehend the anomaly of one of its members, we must first appreciate the grandeur of the other two. For inhabitants of the northern hemisphere, Alpha Centauri is more of a legend, an astronomical fact, than a tangible celestial object. It is simply hidden below the horizon. However, if you find yourself in southern latitudes, for example, in Australia, Chile, or South Africa, you will witness a completely different picture. There, in the velvety blackness of the night sky, this system is a reality. Along with its neighbor Beta Centauri, it forms a bright pair that points to the well-known asterism of the Southern Cross. Ancient mariners and travelers navigated by it as a celestial compass. The Arabs gave it the name Rijal Kentaurus, which translates to foot of the centaur, emphasizing its place in the mythological constellation. To the naked eye, Alpha Centauri appears as a single but very bright star. In reality, it is the third brightest point in the entire night sky, surpassed only by Sirius and Canopus. Its steady and calm yellow-white light strongly resembles the radiance of our own daytime star. There is nothing surprising in this, because, as we will soon see, the similarity here is not just visual. For centuries, people gazed at this light, seeing it as just a single star. It was a simple and clear spectacle. But one of the greatest revolutions in our understanding of the universe began precisely when we realized that our eyes see far from everything. The first step towards unraveling the true nature of Alpha Centauri was taken in the middle of the 15th century, in 1752. French astronomer Nicolas Louis de Lacaille, while observing at the Cape of Good Hope, directed his telescope at this bright point and made a discovery. It is not one star, but two tiny disks of light located very close to each other. The realization that many stars are in reality pairs, or even more complex systems, became one of the cornerstones of astronomy. It demonstrated that our solar system, with its single central star, might not be the rule, but rather the exception. The galaxy turned out to be filled with stellar families, bound by invisible ties of gravity. These two stars were named Alpha Centauri A and Alpha Centauri B. Let us get acquainted with them more closely, as they are key to understanding everything happening in this system. Let's start with the main star of Alpha Centauri. If we had the opportunity to travel through space and pick stars that most resemble our home, this one would be among the first on the list. Astronomers classify it as a G2V spectral class star. This seemingly dry combination of letters and numbers actually carries a lot of information. The letter G means it is a yellow dwarf, a star with a surface temperature of about 5,790 Kelvin, which is practically identical to our Sun. The number 2 refines its position within this class, and the Roman numeral 5 indicates its membership in the main sequence stars. This means it is in its prime, steadily burning hydrogen in its core and converting it into helium, just as our Sun is doing right now. It is slightly more massive than our star. Its mass is approximately 1.1 solar mass. It is also slightly larger in size. Its radius exceeds the solar radius by approximately 1,223,000 times. Because of this, it shines brighter. Its total luminosity is about 1.5 times greater than that of the Sun. One could say that Alpha Centauri A is like an older, slightly larger, and more powerful brother to our Sun. A very similar, but still not exact, copy. Now let's look at its companion, Alpha Centauri b. It is a K1b spectral class star. The letter K indicates it is an orange dwarf, a star that is cooler and dimmer than G-class yellow dwarfs. Its surface temperature is approximately 5,260 Kelvin. It is smaller and lighter than its neighbor. Its mass is about 90% of our Sun's mass, and its radius is about 86,300 kilometers. As a result, it shines significantly dimmer. Its luminosity is only about half of the Sun's. If we continue our family analogy, then Alpha Centauri b is the younger, more reserved and modest brother in this pair. And these two luminaries, a yellow-white giant and its orange satellite, perform an endless cosmic dance. They do not just coexist in space. They are bound by gravity and revolve around a common center of mass, which astronomers call the barycenter. Imagine two dancers of different weights holding hands and spinning. The point around which they rotate will be shifted towards the heavier partner. The same thing happens here. The barycenter of the Alpha Centauri A and B system is shifted closer to the more massive star A. Their dance is very unhurried. They complete one full revolution in 79.91 Earth years. Think about it. An entire human life is just 1 year in the Alpha Centauri system. The orbit of their movement is highly elongated and elliptical. This means the distance between the two stars is constantly changing. At the closest point of their orbit, called periastron, they approach each other to a distance of 11.2 astronomical units. An astronomical unit is the average distance from the Earth to the Sun. So, at the moment of maximum approach, these stars are approximately as far from each other as Saturn is from our Sun. But at the farthest point of the orbit, at a pastron, they diverge to a huge distance of 356 astronomical units, which is farther than from the Sun to Neptune or even Pluto. This dynamic creates incredibly complex conditions. And here, let us allow ourselves a small thought experiment to truly feel the scale of what is happening. Suppose one of these stars, say Alpha Centauri A, has a planet similar to Earth, located at a comfortable distance. What would the sky look like from its surface? Firstly, there would be two suns in the sky, one's own native one, almost like ours, and the second, Alpha Centauri b, would look like an unimaginably bright star, unparalleled in our sky. Its apparent brightness would change over the 80-year cycle. When it was at its farthest point, its glow would be comparable to a -1 stellar magnitude. For comparison, the full moon in our sky has a brightness of about -13. That is, even at maximum distance, the second sun would shine hundreds of times brighter than our moon, and at the moment of maximum approach, its brightness would reach -21 stellar magnitude. This is already thousands of times brighter than the moon. It would be a dazzling orange diamond in the sky, capable of casting clear shadows even during the day. The light on such a planet would never be purely white or yellow. It would be a constantly changing mixture of the yellow-white glow from star A and the orange from star B. Sunsets and sunrises would be unimaginably beautiful. Sometimes both suns would set simultaneously, painting the sky in complex peach and golden hues. Sometimes one would set, and the other would remain high in the sky, creating a state of eternal twilight instead of night. The concept of night, as we understand it, could occur only for short periods when both luminaries were below the horizon, and the seasons on such a planet would be determined not only by its axial tilt, as on Earth. They would also be supplemented by the great 80-year cycle associated with the approach and recession of the two stars. When the stars converged, the planet would receive significantly more heat, which could cause global orbital summer periods. And when they diverged, cooling would set in. Life, if it were to arise there, would have to adapt to these long climatic cycles, measured in entire generations. This is the majestic, complex, and dynamic picture we get. Simply by looking through a telescope at one bright point in the constellation Centaurus, two mighty stars, two almost identical twins of our Sun, are forever locked in a gravitational embrace. And for almost 2 centuries after the discovery of the local system, astronomers were confident that this picture was complete, that the Alpha Centauri system was a classic binary star, bright, beautiful, and understandable. But the universe is rarely so simple. And in this seemingly complete story lay yet another, a third chapter. A chapter about an invisible companion. The fact is that when astronomers learned to measure the movement of stars with high precision, they noticed a peculiarity. The entire system of pairs A and B moves through the galaxy as a single unit. This phenomenon is called proper motion. Imagine observing a flock of birds flying in the distance. They all move in approximately the same direction and at the same speed. Similarly, stars belonging to the same system should travel through the Milky Way together. And so, studying star charts, astronomers ask themselves, are there other stars nearby, even very dim ones, that would move in exactly the same way as this bright pair? Is someone else, unnoticed, traveling alongside this brilliant duet, who is also part of this family? This question served as the starting point for the search, a search that was crowned with success and revealed to us the strangest and most mysterious member of this stellar family. Against this magnificence, this radiance of two suns, somewhere on the periphery in deep shadow, hid a third companion. And it is precisely its nature, its dimness, and its secrets that are the subject of our conversation today. Why, in the midst of this feast of light, does a realm of almost complete darkness exist? To understand this, we need to leave the bright center of the system and venture to its cold and distant outskirts. We left the brilliant pair Alpha Centauri A and B in their eternal gravitational dance. For decades, this binary system was an object of admiration and study, a self-sufficient and, it seemed, complete picture of our closest stellar neighborhood. But at the beginning of the 20th century, astronomers' instruments became accurate enough to notice subtle details that had escaped the attention of previous generations. One such detail was the proper motion of stars, their slow but measurable displacement against the background of distant galaxies. Studying this movement, scientists concluded that stars belonging to the same gravitational system should travel through space together, like a fleet of ships. It was this method that led to a great discovery. In 1915, Scottish astronomer Robert Thorburn Ayrshire Innes, director of the Union Observatory in Johannesburg, South Africa, was engaged in meticulous work. He compared photographic plates of the same section of the sky taken several years apart. This process, known as blink comparison, allowed for the identification of objects that had changed their position. Innes noticed an extremely dim star that stood out in no way. But when he compared its position in images from different years, he discovered an astonishing fact. This tiny point was moving across the sky at the same speed and in the same direction as the blindingly bright Alpha Centauri. This could not be a mere coincidence. The probability of two unrelated stars at different distances from us having identical proper motion is negligibly small. Innes realized that he had found the third, long-sought member of the system. He named this star Proxima Centauri, Proxima, from the Latin word meaning nearest. And indeed, subsequent measurements showed that due to its position in an elongated orbit around the central pair, this small star is currently slightly closer to Earth. It is our outpost, our closest neighbor in the boundless ocean of space. But what is surprising is that its discovery did not cause a sensation like the discovery of a new planet. It was quiet, academic, because Proxima Centauri turned out to be completely unlike its bright sisters. It was a representative of a completely different class of stars, a class that dominates the galaxy but remains practically invisible to us. Proxima Centauri is a red dwarf. To understand what this is, let's delve into astronomical classification. Stars are divided into spectral classes, denoted by the letters O, B, A, F, G, K, M. This sequence goes from the hottest, most massive, and brightest stars, blue giants of class O, to the coldest, smallest, and dimmest, red dwarfs of class M. Our Sun is a G-class star, a yellow dwarf, located somewhere in the middle of this list. Alpha Centauri A, as we remember, and Alpha Centauri B, a bit cooler, are class K. But Proxima Centauri belongs to class M5VA. This is almost at the end of the scale. Let's translate these symbols into understandable language. The letter M tells us that it is a very cold star. Its surface temperature is only about 3,420 Kelvin. This is more than twice as cold as the surface of the Sun. Due to such a low temperature, it emits light mainly in the red and infrared parts of the spectrum, which is why it is called a red dwarf. The letters Va indicate that it is a flare star with emission lines in its spectrum. But we will talk about this turbulent characteristic of its nature later. For now, what is important for us is that it is a dwarf. And this word is used here not for decoration. The size and mass of Proxima Centauri are truly modest. Its mass is only about 12% of the Sun's mass, or more precisely, 123 thousandths of a solar mass. This is very close to the theoretical lower limit for a star's mass. If it were even slightly lighter, by about a third, the pressure and temperature in its core would no longer be sufficient to initiate a stable thermonuclear reaction of hydrogen fusion, and then it would become not a star, but a brown dwarf, a failed star that shines only through slow contraction. So, Proxima hovers on the very edge of what can be called a star at all. Its diameter is also strikingly small, only about 1/7 of the Sun's diameter. This is approximately 191,000 kilometers. To better imagine this, let's compare it to the gas giant planet in our solar system, Jupiter. Jupiter's diameter is about 140,000 kilometers. That is, the closest star to us is only 1.35 times larger than Jupiter in diameter. If we could place Proxima Centauri in the position of our Sun, it would appear in the sky as a tiny, dim, cherry-red disk. It is these fundamental characteristics, small mass and low temperature, that are the reason for its invisibility. Let's return to the campfire analogy. The brightness of a campfire depends on two things: how much wood is put into it, analogous to mass, and how hot it burns, analogous to temperature. Proxima Centauri has little wood, and it burns very coldly. As a result, its luminosity, the total amount of energy it emits per second, is simply negligible compared to the Sun. It is only 0.17% of the solar luminosity. If our Sun were a powerful spotlight of 100,000 watts, then Proxima Centauri would be a tiny LED of 17 watts. This colossal difference in luminosity directly affects how we see these stars from Earth. Astronomers measure the brightness of objects in the sky using the stellar magnitude scale, which we have already mentioned. This scale is logarithmic and slightly counterintuitive. The larger the number, the dimmer the object. The limit of visibility for the human eye under ideal conditions is approximately 6th magnitude. Anything with a magnitude of 7, 8, 9, and so on is invisible to us. The apparent magnitude of Proxima Centauri is 11.13. This is hundreds of times weaker than the threshold of human vision. Even if you were in the darkest spot on the planet on a clear, moonless night and knew exactly where to look, you would see nothing, just an empty space in the sky. To discern our closest neighbor, a telescope is needed, and not a very weak one. Binoculars will likely not help. An instrument with an objective lens diameter of at least 8 centimeters is required, and even with it, Proxima will appear as only a barely noticeable reddish point. Now let's imagine we are not on Earth, but on a hypothetical planet orbiting Alpha Centauri A or B. From that distance, Proxima Centauri would appear as a star of approximately 5th magnitude. That is, it would be visible to the naked eye, but very dim, at the very limit of visibility. It would be one of thousands of similarly faint stars, and nothing would betray it as a member of the same system. Imagine entire civilizations could live and develop under the light of two suns, not even suspecting that their system has a third, distant, and almost invisible companion. And here we come to the most important point. Red dwarfs like Proxima are not some kind of exotic thing, they are the norm. Our Milky Way galaxy contains, according to various estimates, from 200 to 400 billion stars, and about 3/4 of them are precisely these dim, cold, and small red dwarfs. When we look at the night sky, we see only a thin layer of cream, the rarest, most massive, and brightest stars that are visible from vast distances. It's like judging the population of a large city by only celebrities and media personalities. And the overwhelming majority of the simple inhabitants of the galaxy, these billions of red dwarfs, remain invisible to us. There are so many of them that despite their tiny individual masses, they collectively constitute a significant portion of all stellar mass in the galaxy, about 30%. They are the quiet, invisible, but fundamental foundation of the stellar population of the universe. and Proxima Centauri is our chance to study this most common type of star in minute detail, as it is right under our noses. So, we have answered the first, most superficial layer of our question. We do not see Proxima Centauri because it is a red dwarf. It is too small, too cold, and consequently, too dim. This is a simple physical fact, but it immediately raises the next, much deeper question. Why is it like that? What exactly is happening in its depths? What makes it so strikingly different from its sisters and from our Sun? Why does its thermonuclear furnace operate in such an economical mode? To answer this, we will have to journey into the very heart of the star and understand the laws of physics that govern its life. This is a journey into a world of colossal pressures, incredible temperatures, and the most fundamental process in the universe, thermonuclear fusion. We have established that Proxima Centauri is a red dwarf, a tiny and cold star whose dimness makes it invisible to us. This is a fact. But science never stops at the simple. It always strives for the answer to the question, why? Why is Proxima Centauri so different from its sun-like neighbor, Alpha Centauri A? Both stars were born from the same giant cloud of gas and dust approximately 4.85 billion years ago. They are of the same age, formed from the same material. So what determines such different fates? The answer lies in one single fundamental parameter: mass. Mass is the alpha and omega of stellar evolution. It dictates everything: the star's size, its temperature, color, brightness, and ultimately its lifespan and how it will die. To understand how this works, we need to look inside the very heart of a star, into its core. It is there that the thermonuclear reactor, the source of all its energy, is located. Let's break down this process using our Sun as an example. Then we will see how it changes in the conditions of a red dwarf. Imagine the Sun's core. It is a region of unimaginable conditions. The temperature here reaches 15 million degrees Celsius, and the pressure is 265 billion times greater than the atmospheric pressure on the surface of Earth. The density of matter here is 150 times higher than the density of water. Under such conditions, matter cannot exist in the states we are familiar with: solid, liquid, or gaseous. It turns into plasma, a soup of atomic nuclei and freely moving electrons. These are mainly hydrogen nuclei, that is, single protons. Gravity, generated by the Sun's colossal mass, tries to compress this core, to crush it into a point. But this compression is resisted by the enormous pressure created by thermonuclear reactions. The star exists in a state of fragile equilibrium called hydrostatic balance. Gravity pushes inward, and the energy born in the core pushes outward. This balance keeps the star stable for billions of years. So, what are these reactions that produce so much energy? It is a process called the proton-proton cycle. Simplified, it looks like this: 4 hydrogen nuclei, 4 protons, merge together in several stages to form one helium nucleus. But here's what's interesting. The mass of one helium nucleus is slightly less than the total mass of the 4 initial protons. Where does this missing mass go? This is where Albert Einstein's famous formula, E equals mc squared, comes into play. The vanished mass, this tiny mass defect, is converted into a pure amount of energy. And although the mass lost in each individual reaction is negligible, in the Sun's core, about 600 million tons of hydrogen turn into helium every second. This releases energy equivalent to the explosion of trillions of hydrogen bombs per second. This energy, in the form of gamma rays and neutrinos, is what makes the Sun shine. Now let's go back to Proxima Centauri and see how everything changes. When a star's mass is only 12% of the Sun's, the key difference lies in the strength of gravitational compression. Since Proxima's mass is much smaller, its gravity is weaker. It cannot compress its core as much as the Sun does. As a result, the pressure in its core is significantly lower. And if the pressure is lower, then the temperature there is also lower. Estimates show that the temperature in Proxima Centauri's core is only about 4 million degrees Celsius, almost 4 times lower than in the Sun's core. And this is the decisive factor. The rate of thermonuclear reactions is extremely sensitive to temperature. Protons, as we remember, are positively charged, and therefore they repel each other. For them to merge, they need to overcome this electrostatic barrier. A quantum effect called tunneling helps them do this. But even with it, the higher the temperature, the faster the protons move, the more often they collide, and the higher the probability that they will merge. Let's use an analogy. Imagine a large room full of blindfolded people moving chaotically. We need them to collide and shake hands. The speed of this process will depend on two things: the density of people in the room and the speed of their movement. The sun's core is a very crowded room where people are moving at tremendous speed. Collisions happen very frequently. Proxima Centauri's core is also a crowded room, but the people in it move much more slowly, almost at a leisurely pace. Collisions leading to a handshake, meaning a thermonuclear reaction, happen much, much less often. How much less often? The rate of energy production in a star's core is proportional to the temperature approximately to the fourth power. This means that even a small decrease in temperature leads to a catastrophic drop in energy release. Since the temperature in Proxima's core is almost 4 times lower than in the Sun's, the rate of thermonuclear fusion there is not 4 times lower, but hundreds of times lower. Another analogy with an internal combustion engine can be used. The Sun is a powerful, highly boosted engine of a racing car. It operates at maximum revs, burns a huge amount of fuel, and produces colossal power. Proxima Centauri is a tiny, economical engine from a lawnmower. It operates at the lowest revs, consumes fuel literally drop by drop, and consequently produces very little power. It is this slow, leisurely rate of thermonuclear fusion that is the fundamental reason for the dimness of red dwarfs. They simply produce energy thousands of times slower than sun-like stars. And this energy, born in the core, then has to travel a long way to the surface. And here we encounter the second key difference between Proxima and the Sun: the method of energy transfer. In the Sun's core, energy is born in the form of high-energy gamma quanta. These photons cannot escape directly. They are constantly absorbed and re-emitted by plasma particles, wandering chaotically in the so-called radiative transfer zone. The path of one photon from the core to the Sun's surface can take hundreds of thousands of years. Only in the outer third of the Sun does the plasma become sufficiently opaque, and energy begins to be transferred in another way, by convection. This is like boiling water in a pot. Hot plasma streams rise, give off heat, cool down, and sink. But in a red dwarf like Proxima Centauri, it's different. Due to its low mass and relatively low temperature, its interior is much less transparent to radiation, so radiative transfer hardly works there. Instead, the entire star, from the core to the surface, is engulfed in convection. Imagine this. All the matter inside Proxima Centauri is in constant motion, in continuous mixing. It's like a pot of soup that is constantly and very thoroughly stirred. Hot substance from the core itself, enriched with helium, a product of thermonuclear reactions, rises to the surface, and cooler substance from the surface, rich in fresh hydrogen fuel, sinks down directly into the core, where it reacts. This fundamental difference has two astonishing consequences. Firstly, it directly affects the star's magnetic activity, which, as we will see later, is its main and most dangerous secret. And secondly, and this is simply mind-boggling, this makes red dwarfs practically immortal by human standards. In a sun-like star, thermonuclear reactions occur only in the very core. The hydrogen in the outer layers will never reach this furnace. This means that the Sun will only be able to use about 10% of its entire hydrogen reserve. When the hydrogen in the core runs out, the Sun will begin to die, turning into a red giant. But Proxima Centauri, thanks to complete mixing, can use almost all of its fuel, all of its hydrogen. Its fuel tank is used 100%. Combine this fact with its extremely slow fuel burning. What will be the result? An incredible lifespan. The estimated lifespan of our Sun on the main sequence is about 10 billion years. It is currently about 4.6 billion years old, so it has lived approximately half of its active life. But the estimated lifespan of a red dwarf like Proxima Centauri is several trillion years. Trillions. This is hundreds of times longer than the current age of the universe, which is about 13.8 billion years. Think about it. Proxima Centauri is a dim, invisible dot in our sky. It is a witness to the deep future. It will shine almost as it does now when our Sun has long since turned into a white dwarf and cooled down. It will shine when the Andromeda Galaxy collides with the Milky Way. It will even shine when the last massive stars in the universe have long since exploded and faded away. The era when the universe was filled with bright stars is just a brief moment at its beginning. But the future of the universe belongs precisely to such dim, economical, and long-lived red dwarfs like Proxima. Its quiet, barely noticeable light is the light of eternity. And understanding this fact changes everything. We stop seeing it as just a dim star. We begin to see it as a time machine, looking into an era that humanity will never see. And all of this is a direct consequence of the laws of physics that operate in its tiny, slow-working heart. In the previous chapter, we looked into the very heart of Proxima Centauri and discovered that its dimness is a direct consequence of its low mass. Slow thermonuclear reactions and complete convective mixing of matter make it extremely economical. But these same processes lead to a consequence that is hard to even imagine. They grant red dwarfs an almost eternal life. Let's break down this idea further because it overturns our intuitive ideas about stars and time. When we talk about lifespan, we usually mean the active phase of a star's existence, the so-called main sequence lifetime. This is the period while hydrogen burns stably in the star's core, turning into helium. It is in this phase that our sun and the vast majority of stars we see in the sky are. The duration of this phase directly depends on two factors: the amount of available fuel and the speed at which this fuel is consumed. Let's use our car analogy again. Imagine we have two cars. The first is a powerful sports car with a huge engine. This is our sun. It has a large fuel tank, say 100 liters. But due to its power, it burns fuel at an incredible rate, consuming, for example, 20 liters per 100 kilometers. The second car is a small, economical city car. This is Proxima Centauri. Its fuel tank is much smaller, only 12 liters, which corresponds to its mass being 12% of the sun's. But its tiny engine is so efficient that it consumes only 1 liter per 100 kilometers. Now let's calculate which car will go further. The sun sports car will be able to travel only 500 kilometers before its tank is empty. But Proxima, the small engine car, despite its tiny tank, will travel a whole 12,000 kilometers. The difference is colossal. But even this analogy is not entirely complete because it doesn't account for the most important fuel mixing mechanism. Let's complicate it. Imagine that the fuel pump in the sun sports car can only draw gasoline from the very bottom of the tank, using only 10% of the total volume. The remaining 90 liters will remain unused. In this case, its actual mileage will be only 50 kilometers. But Proxima, the small engine car, has a brilliant system that constantly mixes all the gasoline in the tank. This is our complete convection. Thanks to it, the car will be able to use all 12 liters to the last drop. Its mileage will remain 12,000 kilometers. Now compare 50 kilometers for a powerful sports car versus 12,000 for a modest, small engine car. The difference becomes simply astronomical. This is exactly what happens with stars. The sun, in its lifetime, will only be able to burn about 10% of its hydrogen in its core. When this fuel runs out, in about 5 billion years, its core will contract and heat up. The outer layers will expand, and the sun will turn into a red giant. Its size will increase so much that it will engulf Mercury, Venus, and possibly even Earth. After this turbulent but short phase, it will shed its outer envelopes, forming a beautiful planetary nebula, and in its place will remain a tiny and super-dense object, a white dwarf, which will slowly cool down over trillions of years. This is the path of sun-like stars. And what awaits Proxima Centauri? Its fate will be much less dramatic, but much longer. Thanks to complete convective mixing, it will slowly and methodically burn almost all of its hydrogen, turning it into helium. This process will last an unimaginably long time. According to current estimates, the lifespan of Proxima Centauri on the main sequence will be from 2 to 5 trillion years. Let's just try to grasp this figure. A trillion is 1,000 billion. Our universe is only 13.8 billion years old. This means that Proxima Centauri will live hundreds of times longer than the universe itself has existed to date. The entire history of the cosmos from the Big Bang to our day is just a tiny introductory paragraph in the epic life story of this small star. When Proxima Centauri exhausts most of its hydrogen, it will not turn into a red giant. Its mass will simply not be enough to ignite helium fusion reactions in the core. Instead, it will slowly contract and heat up. As the proportion of helium in it increases, it will become hotter and brighter than it is now. At the peak of its evolution, after trillions of years, it will turn into a so-called blue dwarf, a hypothetical type of star that does not yet exist in the universe. After all, no red dwarf has yet lived long enough to reach this stage. It's like describing what 100-year-old turtles would look like when there hasn't been a single turtle older than 1 year in the world yet. After the blue dwarf stage, when all the hydrogen is finally depleted, Proxima Centauri will smoothly and without any cataclysms contract into a white dwarf, composed mainly of helium. And then, like the remains of our sun, it will slowly, endlessly, cool down in the empty and dark universe of the future, eventually turning into a cold and dark object, a black dwarf. This prospect of deep time makes us look at the cosmos in a new way. We are used to thinking of the universe as a place of turbulent and rapid processes, supernova explosions, galaxy collisions, the birth and death of stars. And this is indeed true for massive stars. Their lives are bright but short. They quickly burn their fuel and die, enriching the cosmos with heavy elements from which new stars and planets like ours are later formed. They are the engines of cosmic evolution, but red dwarfs are the keepers of time. They play the long game. They are the future of the universe. There will come a time, which astrophysicists call the epoch of stellar degeneracy. 100 trillion years after the Big Bang, the process of active star formation in galaxies will cease. The gas from which stars are born will be depleted. All massive stars will have long since faded, and the only sources of light in the cold and expanding universe will be precisely red dwarfs, which will still be leisurely burning their hydrogen reserves. Imagine this picture. Galaxies, devoid of their bright spiral arms, will turn into dark clusters of dim red lights and cooling white dwarfs. The sky from any planet will look completely different, not a scattering of bright diamonds, but a barely perceptible red glow emanating from these eternal stars. This is precisely why studying Proxima Centauri is so important. It is not just our closest neighbor, it is a window into the distant future. By studying it today, we are studying the physics of objects that will dominate the universe on timescales beyond our imagination. This fact is also of great importance for the question of the search for extraterrestrial life. On the one hand, the incredible lifespan of red dwarfs gives hypothetical life on their planets a huge amount of time to arise and evolve. If complex life developed on Earth in 4 billion years, then imagine what evolution could achieve in 100 billion or even 1 trillion years. This allows for the wildest fantasies. On the other hand, as we will soon see, this medal has a flip side. Young red dwarfs like Proxima can be extremely active and unstable, making their planetary systems extremely inhospitable. Perhaps life can only arise on very old, calm red dwarfs, which we cannot yet observe. Thus, Proxima Centauri teaches us a lesson of cosmic humility. We, with our short lives on a planet around a star with a finite fuel supply, are merely a fleeting phenomenon. And the true marathoners, the true long-livers of the universe, are these inconspicuous, invisible red dots scattered throughout the cosmos. Their dim light is not a sign of weakness, it is a sign of incredible efficiency and endurance. They have chosen a different strategy, not to burn brightly, but to shine for a long time. And in this strategy, they are absolute champions. Understanding this fact is the key not only to unraveling the mystery of Proxima's invisibility, but also to understanding the fundamental structure and future fate of our entire universe. We don't see it because our vision and consciousness are tuned to the bright and fast-moving. And Proxima Centauri is the quiet whisper of eternity that can only be heard if you listen very carefully. So far, we have spoken of Proxima Centauri as a dim, weak, almost invisible star. And from the perspective of human vision, this is absolutely true. Our eyes, formed over millions of years of evolution under the light of a yellow sun, are surprisingly perfect, but at the same time, very narrowly specialized instruments. They perfectly perceive that tiny portion of the electromagnetic spectrum that we call visible light. But this visible light is just the thinnest slit in a huge window through which the universe communicates with us. Beyond this narrow range from violet to red lie entire worlds of radiation that our eyes cannot detect. Radio waves, microwaves, ultraviolet, X-rays, and, especially important for our story, infrared radiation. It is here, in the world invisible to us, that another answer to the question lies. Why does Proxima Centauri seem so dim to us? It's not just that it produces little energy, it's also in what form it radiates that energy. Let's go back to physics. Any object with a temperature above absolute zero emits electromagnetic waves. This process is called thermal radiation. The nature of this radiation, i.e., at what wavelength it will be most intense, directly depends on the object's temperature. There is a fundamental physical law called Wien's displacement law, which states, the hotter an object, the shorter the wavelength at which its radiation peaks. Imagine a piece of metal that we start heating. At first it's just warm and doesn't glow in the visible range, but if you look at it through a thermal imager, which detects infrared radiation, you will see that it glows brightly. Continuing to heat the metal, we will see it first become dark red, then bright orange, then yellow. And finally, at very high temperatures, it will glow dazzlingly white or even bluish. What we observe is the shift of the radiation peak from the infrared region into the visible and further towards shorter wavelengths. Now let's apply this principle to stars. Our Sun has a surface temperature of about 5,800 Kelvin. At this temperature, its radiation peaks exactly in the middle of the visible range, in the green part of the spectrum. It is to this light that our eyes have adapted, which is why we perceive it as white. The Sun effectively radiates in the range that we see. Now let's look at Proxima Centauri. Its surface temperature, as we remember, is only about 3,000 Kelvin. According to the law of displacement of Wien, the peak of its radiation will be located not in the visible, but in the near-infrared region of the spectrum, at a wavelength of about 960 nanometers. For comparison, the human eye sees up to approximately 700 nanometers. This means that the vast majority of photons born from Proxima Centauri fly past us without causing any reaction in the retina of our eye. We see only the very edge, the very tail of its energy distribution, which enters the red part of the visible spectrum. Let's use an analogy with sound. Imagine there are two singers. One, like the Sun, sings in a middle register, which we hear perfectly. His voice seems loud and clear to us. The second singer, like Proxima Centauri, sings in a very low infrasonic range at frequencies that our ears simply cannot pick up. We can only hear the highest overtones of his voice, which barely enter the audible range. It will seem to us that he sings very quietly, almost in a whisper. But in reality, if we had special microphones sensitive to infrasound, we would realize that his voice is incredibly powerful. It simply sounds at a different frequency. It's the same with Proxima Centauri. To our eyes, it is a dim, barely noticeable speck of light, but if we could see in the infrared range, the picture would change dramatically. In near-infrared light, Proxima Centauri is one of the brightest stars in the sky. It shines much brighter than many stars that appear to us as giants in visible light. We don't see it not because it doesn't shine. We don't see it because our biological detectors are tuned to a different wavelength. This realization became a revolution in astronomy. In the 20th century, scientists realized that by limiting themselves to visible light, they were missing a huge amount of information about the universe. The era of all-wave astronomy began. Telescopes were created that could see in radio, infrared, ultraviolet, X-ray, and gamma ranges. And this completely changed our view of the cosmos. Infrared telescopes played a key role in studying cold objects such as red dwarfs, brown dwarfs, and molecular clouds where new stars are born. Ground-based observatories face a problem. Earth's atmosphere, especially the water vapor in it, strongly absorbs infrared radiation. Therefore, the best infrared observatories are built high in the mountains, in dry deserts, such as telescopes in Hawaii or in the Atacama Desert in Chile. But a real breakthrough occurred when we were able to launch infrared telescopes into space, beyond the interfering atmosphere. Spacecraft such as Spitzer and Herschel, and in our time, the greatest of them, the James Webb Space Telescope, have revealed the universe to us in its true invisible splendor. For these telescopes, Proxima Centauri is not a dim peripheral star, but the brightest object, an ideal target for study. James Webb, with its enormous mirror and highest sensitivity in the infrared range, can study Proxima Centauri and its planetary system with unprecedented detail. It can analyze the spectrum of its light to determine the chemical composition of its atmosphere. It can try to directly see the light reflected from its planets, or even detect thermal radiation from their surfaces. What is almost complete darkness to us is a bright scene for it, on which a cosmic drama unfolds. This shift in perception also has a profound philosophical meaning. It teaches us that our human perception of the world is not absolute. It is only one of many possible points of view. A bee sees the world in ultraviolet, and for it, flowers look completely different, with patterns indicating the way to nectar. A snake sees the thermal radiation of its prey. And similarly, to understand the universe, we must learn to look at it through the eyes of telescopes tuned to different ranges. Thus, to the question of why we do not see Proxima Centauri, we can now give a more complete and nuanced answer. First, it produces much less energy than the Sun due to its small mass and slow nuclear fusion. Second, the energy that it does produce, it primarily emits in the infrared part of the spectrum, invisible to us. The combination of these two factors leads to our nearest stellar neighbor remaining a ghost in the night sky for us. This story is not about darkness, but about light that we are not adapted to see. It is a reminder that reality is always richer and more complex than the picture painted for us by our senses. To truly understand our neighbor, we needed to go beyond our biological limitations and create new eyes capable of seeing in infrared light. And when we did, Proxima Centauri transformed from an invisible point into a bright beacon. But this beacon, as we will soon learn, shines with an unsettling, fierce, and potentially deadly light. We have unraveled the mystery of its dimness, but its main and most alarming secret awaited us. We have come a long way to understand the nature of Proxima Centauri's invisibility. We learned that it is a tiny and cold red dwarf, a star that conserves energy and will live for trillions of years. We understood that most of its light is emitted in the infrared range, invisible to us. All this paints a picture of a calm, stable, even somewhat sleepy star, a quiet, inconspicuous neighbor, living its unhurried life on the outskirts of the stellar system. And for decades, this has been the astronomers' perception of red dwarfs. They were considered ideal candidates for the role of suns for habitable worlds. After all, their longevity would give life almost infinite time to develop. But the more closely we looked at these quiet neighbors, the clearer it became that behind this facade of calmness lay a turbulent and unpredictable character. And Proxima Centauri turned out to be the most striking and closest example of this duality. And so we have come to its main secret. Proxima Centauri is not just a red dwarf, it is a flare star, and its flares possess such furious power that they can turn any nearby world into a sterile desert. What is a stellar flare? In essence, this phenomenon strongly resembles solar flares, which also occur on our Sun. However, on Proxima Centauri, they acquire a completely different catastrophic scale. To understand their causes, it is necessary to look again into the internal structure of the star, or rather, into its magnetic field. The magnetic field is generated by the star in a process called a stellar dynamo. It requires two main components: convection, which means the mixing of electrically conductive plasma, and rotation. Our Sun possesses both of these components, but, as we recall, convection in it occurs only in the outer third. The deep layers, i.e., the radiative transfer zone, do not rotate the same way as the outer convective layers. This difference in rotation speeds, known as differential rotation, stretches and twists the magnetic field lines like rubber bands. Sometimes these bands get tangled and break out, forming sunspots, and when the tension reaches a critical point, they abruptly break and reconnect. This process, called magnetic reconnection, releases a huge amount of accumulated energy, manifesting as a burst of charged particles and powerful radiation across the entire spectrum, from radio waves to X-rays. Now let's look at Proxima Centauri. First, as we already know, it is fully convective. Its entire mass, from the core to the very surface, is in a state of continuous boiling and mixing. This generates much more chaotic and tangled plasma movements than on the Sun. Second, Proxima Centauri rotates on its axis quite slowly. One rotation takes approximately 83 Earth days. For comparison, the Sun rotates at the equator in about 25 days. It might seem that slow rotation should weaken the dynamo effect, but here the complex interaction between deep convection and rotation comes into play. It turns out that even leisurely rotation in combination with such intense convection can generate extremely strong and tangled magnetic fields, which are on average much more powerful than those of the Sun. The surface of Proxima Centauri is dotted with giant stellar spots, regions with anomalously strong magnetic fields capable of occupying up to 20% of its entire surface area. For comparison, even during periods of maximum activity, sunspots cover less than 1% of the Sun's surface. These enormous magnetic structures are constantly changing. Turbulent plasma flows stretch and twist their field lines, and when they reach a critical point, a flare occurs. But the scale of these phenomena is incomparable to what we see on the Sun. A solar flare can increase the Sun's total brightness by a fraction of a percent, and only for a very short time. For us on Earth, this is practically unnoticeable, although it can lead to auroras and disruptions in satellite operation. At the same time, a flare on Proxima Centauri can increase its visible brightness by 10, 100, or even 1,000 times. Imagine a star that is usually barely visible in a telescope, but suddenly for a few minutes or hours turns into a quite bright object in the sky. The first hints of such a boisterous character of Proxima appeared in the mid-20th century when astronomers noticed its irregular brightness fluctuations. However, the true scale of the phenomenon became clear only with the advent of modern instruments that can continuously monitor the star. The results of these observations turned out to be simply astonishing. Proxima Centauri experiences several powerful flares a day on average, but sometimes there are also so-called superflares. In 2016, astronomers working with the ALMA telescope in Chile accidentally recorded one of them. In just 10 seconds, Proxima's brightness in the millimeter radio wave range jumped 1,000 times. This flare was 10 times more powerful than any similar flare ever recorded on the Sun. But even this was not the limit. The most dramatic event was recorded on May 1, 2019. A group of astronomers led by Meredith McGregor from the University of Colorado Boulder conducted coordinated observations of Proxima Centauri using 9 telescopes simultaneously, including the Hubble Space Telescope. They were incredibly lucky. They witnessed the most powerful flare ever observed, not only on Proxima, but on any star of this type. In just 7 seconds, the star's brightness in the ultraviolet range increased 14,000 times. 14,000 is not a typo. For a few seconds, this tiny dim star turned into one of the brightest ultraviolet sources in the entire sky. The energy released during this flare was 100 times greater than that of any flare recorded on the Sun. Let's use the analogy again to grasp this scale. Imagine that Proxima Centauri is a quiet, inconspicuous person sitting in the corner of a room. And suddenly, without any warning, he lets out a cry louder than the roar of a taking-off jet aircraft. This is precisely the contrast between its normal state and the fury of its flares. This boisterous nature completely changes our perception of it. It is no longer just a quiet neighbor, but a neighbor who suffers from bouts of uncontrollable rage. And this rage has direct and catastrophic consequences for everything around it, especially for its planets. When such a superflare occurs, the star emits not only a powerful stream of electromagnetic radiation, ultraviolet, and X-rays. The flare is often accompanied by a coronal mass ejection, a giant cloud of plasma composed of protons and electrons, which rushes into space at enormous speed. Any planet in a close orbit is subjected to this double blow. First, it is hit by a wave of hard radiation capable of sterilizing any life on its surface and destroying complex organic molecules. Then, a few hours later, a cloud of charged particles reaches it, which strikes its atmosphere like a giant hammer. This process, called atmospheric erosion, can literally strip all of its gas envelope from the planet over millions of years and carry it into space, leaving behind only a bare, lifeless rock. And this fact, the fierce and unpredictable nature of Proxima Centauri, is its main secret. A secret that has long been hidden behind its apparent dimness and inconspicuousness. We hoped to find a calm haven near the nearest star, but discovered a raging storm. This duality, quiet in its normal state and furious during flares, is a fundamental characteristic of many red dwarfs, especially young and relatively fast-rotating ones. Their deep convection generates powerful magnetic fields, which are both the source of their longevity and a curse for their planetary systems. The realization of this fact was a cold shower for many astrobiologists. The hope of finding a habitable world around the most common type of star in the galaxy has clashed with the harsh reality of stellar physics. And this reality became especially dramatic when, in 2016, astronomers reported that directly in the center of this bombardment zone, a planet orbits Proxima Centauri, a planet that, by all formal criteria, is in the so-called habitable zone. This discovery turned an abstract physical problem into a concrete, captivating, and tragic story about a world near a fiery dragon. For centuries, the Alpha Centauri system has stirred the imagination. The stars closest to us, two of which are so similar to the Sun, were considered an ideal place to search for extraterrestrial worlds, our cosmic neighbors. Science fiction writers sent their starships there, populating hypothetical planets with intelligent civilizations. But for scientists, this was only a dream for a long time. The search for planets around other stars, or exoplanets, is a task of incredible complexity. It is akin to trying to see a firefly crawling on the rim of a spotlight from a distance of hundreds of kilometers. Planets do not glow themselves, but only reflect the light of their star. And this reflected light is billions of times weaker than the light of the star itself. It simply drowns in its radiance. Therefore, direct observation of exoplanets is almost impossible, accessible only to the most powerful telescopes and only in very rare lucky cases. Astronomers had to find workarounds, developing indirect methods that would allow them to detect a planet by its influence on its parent star. One of the most successful such methods is called the radial velocity method, or Doppler spectroscopy. The idea is brilliant in its simplicity. When a planet orbits a star, it does not just move on its own. With its gravity, it slightly pulls the star as well. As a result, the star does not stand still, but makes small oscillating movements around their common center of mass, or barycenter. If the star-planet system is like an athlete swinging a heavy hammer on a chain, then the star is the athlete who also sways slightly to maintain balance. Of course, we cannot see these oscillations directly, as they are too small, but we can measure their consequences. When the star moves towards Earth in its mini-dance, the wavelength of its light, according to the Doppler effect, shifts slightly towards the blue part of the spectrum, and when it moves away from us, towards the red. These periodic shifts in spectral lines are the star's barely perceptible breath and indicate the presence of an invisible companion. The speed of these oscillations, the radial velocity, is incredibly small. For a planet the size of Jupiter, it is tens of meters per second, and for a planet the size of Earth, it is only a few centimeters per second. This is the speed of a crawling snail. Imagine the task of measuring the speed of a star located at a distance of 40 trillion kilometers with an accuracy of a pedestrian's speed. It was precisely to solve this problem that the world's most accurate spectrographs were created. One such instrument, a true planet hunter, is called HARPS, High Accuracy Radial Velocity Planet Searcher. It is installed on a 36-meter telescope at the La Silla Observatory in Chile, belonging to the European Southern Observatory. HARPS is a marvel of engineering, capable of measuring stellar radial velocities with an accuracy of 1 meter per second, and it was this instrument that became the main tool in a project that would go down in history. In 2013, a team of astronomers led by Guillem Anglada Escudé from Queen Mary University of London launched an observational campaign called Pale Red Dot. The name is a beautiful reference to the famous photograph of Earth, the pale blue dot, taken by the Voyager 1 probe. Only this time, it was about searching for a world around the closest red star. The project's goal was to systematically and long-term monitor Proxima Centauri using the HARPS spectrograph. Scientists collected data night after night, accumulating measurements of its radial velocity. Their work required incredible patience. Proxima Centauri, as we now know, is a very active star. Its flares and convective plasma movements on the surface create noise in the data that can mimic a planetary signal. It was necessary to separate the wheat from the chaff, to find a weak but regular signal in this chaos, and they found it. Analyzing data collected over several years, scientists detected a barely perceptible but stable periodic signal. The radial velocity of Proxima Centauri oscillated with an amplitude of only 1.4 meters per second, which corresponds to the speed of a leisurely human walk, and these oscillations repeated with a clear period of 11.2 Earth days. Only one object could create such a signal: a planet orbiting the star. On August 24, 2016, an article was published in the journal Nature that caused an explosive effect in the scientific world and far beyond. The Pale Red Dot team officially announced the discovery of a planet around the closest star to the Sun. The planet was designated Proxima Centauri b, or simply Proxima b. This discovery was not just another addition to the catalog of exoplanets, of which thousands had already been discovered by then. This was something absolutely special. It was the discovery of our closest extrasolar world. Until then, the nearest known exoplanet was more than 12 light-years away, and this is only 4.2. For the first time in human history, we could look at the nearest star and know that there, near that dim speck of light, there was a world. Space ceased to be just an abstract emptiness between stars. It acquired a specific, achievable, albeit in the distant future, destination. What did we learn about this planet from the data? The radial velocity signal allowed us to estimate its minimum mass, which was about 1.17 Earth masses. This made Proxima b an Earth group planet, most likely rocky, like Earth, Venus, or Mars. Its orbital period of 11.2 days meant that it was incredibly close to its star, at a distance of only 7.5 million kilometers. This is about 12% of the distance from Earth to the Sun, much closer than Mercury's orbit. At first glance, such conditions seem hellish. At such a distance from a sun-like star, any planet would become a molten ball. But we remember that Proxima Centauri is a dim red dwarf. It emits thousands of times less energy. And this is where it gets interesting. In astrobiology, there is a concept of the habitable zone, or as it is also called, the Goldilocks zone. This is the region around a star where conditions are not too hot and not too cold, but just right for water to exist in liquid form on the surface of a planet with a suitable atmosphere. Liquid water is considered a key component for life, at least in the form we know it. Because of the dimness of red dwarfs, their habitable zones are located very close to them, and calculations showed that Proxima b, despite its close orbit, is located directly within this zone. It receives about 65% of the energy flux that Earth receives from the Sun from its star. This is quite enough to maintain moderate temperatures on its surface, provided it has an atmosphere. This news blew up imaginations. An Earth-sized planet near the nearest star, and also in the habitable zone. It seemed that the hope of finding a second home, a second cradle of life, was about to become a reality. Newspaper headlines around the world screamed about habitable Earth 2.0. Heated discussions began about what this world might look like. But scientists were much more reserved. They perfectly understood that being in the habitable zone is only the very first necessary, but far from sufficient, condition for actual habitability. And in the case of Proxima b, for every encouraging fact, there were several very alarming ones. One of them is tidal locking. Due to the enormous gravitational force of the star at such a close distance, the planet is most likely in synchronous rotation. This means that it is always turned towards its star with the same side, exactly like the moon is always turned towards the Earth. In this case, eternal day and scorching heat reign on one hemisphere of the planet, and eternal night and icy cold on the other. The only potentially habitable zone could be a narrow strip on the border of day and night, the so-called terminator, where eternal twilight reigns. But even the problem of tidal locking pales in comparison to the threat that we have already discussed in detail, the furious, relentless nature of the star itself. The discovery of Proxima b placed this hypothetical world directly in the line of fire. A planet located so close to its parent star receives the full force of its monstrous flares. Every day, it is bombarded by streams of X-ray and ultraviolet radiation hundreds and thousands of times greater than what Earth receives from the Sun. So what is Proxima b actually? A potential paradise garden or a scorched radiation desert? Humanity's hope or a tragic example of a world unlucky with its parent star? The discovery of this planet raised new, even more acute questions rather than providing answers. It turned Proxima Centauri from a simple astronomical object into a real drama with a protagonist planet whose fate is unfolding before our eyes. And to understand this fate, we needed to look at this world near the fiery dragon even more closely. The discovery of Proxima b caused a wave of enthusiasm comparable, perhaps, only to the first steps of man on the moon. The image of a second Earth, our potential cosmic neighbor, was almost instantly formed in the public consciousness. This idea was too tempting to give up. A rocky planet the size of Earth in the habitable zone near the nearest star. But in science, euphoria is quickly replaced by sober and often ruthless analysis. And the more details scientists modeled the conditions on Proxima b, the gloomier the picture became. The dream of a paradise garden began to melt under the pressure of harsh astrophysical realities. It turned out that being in the Goldilocks zone around a red dwarf is like trying to warm yourself by a fire, standing so close that your clothes catch fire from the flying sparks. Let's systematically break down all the factors that turn a potentially habitable world into a most likely lifeless desert. The first and most significant enemy of any possible life on Proxima b is, of course, the furious activity of its star. We have already talked about monstrous flares, but now let's estimate their impact in numbers. In its normal, calm state, Proxima Centauri emits an X-ray radiation flux that is approximately 400 times more powerful than that of the Sun. This fact alone creates an extremely unfavorable radiation background. But during superflares, like the one recorded in 2019, the situation becomes catastrophic. The X-ray flux hitting the planet can increase tens of thousands of times. Any living organism on the surface, unprotected by a thick layer of water or rock, would be instantly destroyed. Hard ultraviolet radiation, especially in the UVC and UVB ranges, destroys complex organic molecules, including DNA. Even if life managed to originate in the ocean, its surface would be completely sterile. Perhaps some extremophiles could survive at great depths near hydrothermal vents, but the development of complex life on land under such conditions is out of the question. But hard radiation is only half the problem. The second, and possibly even more serious threat, is the constant bombardment of the planet by charged particles, the so-called stellar wind. Our Sun also has a solar wind, but Earth is reliably protected from it by its global magnetic field. It, like an invisible shield, deflects most of this stream, forcing it to flow around the planet. Only a small part of the particles breaks through in the polar regions, causing beautiful but harmless auroras. Does Proxima b have such a magnetic field? We don't know. But even if it does, it would face challenges that the Earth's magnetosphere cannot even dream of. The stellar wind from Proxima Centauri is much denser and more energetic, and during coronal mass ejections accompanying flares, a real plasma tsunami crashes down on the planet. The pressure of this stream on the hypothetical magnetosphere of Proxima b would be thousands of times stronger than the pressure of the solar wind on Earth's magnetosphere. Computer simulations conducted by scientists from the Harvard-Smithsonian Center for Astrophysics showed that even a very strong magnetic field would not be able to fully protect the planet. Such a powerful stellar wind would simply compress the magnetosphere, exposing the planet's poles and allowing charged particles to penetrate the upper layers of the atmosphere unimpeded. And here begins a process called atmospheric erosion. Charged particles, colliding with gas molecules in the atmosphere, such as nitrogen, oxygen, or carbon dioxide, ionize them and transfer their energy to them. Having received such a push, these molecules can accelerate to a speed exceeding the second cosmic velocity for this planet and fly off into space forever. It's like a billiard ball knocking other balls out of a pyramid. This process is constant, but during flares, it accelerates thousands of times. Models show that over billions of years of such bombardment, Proxima b could have lost an atmosphere comparable in density to Earth's entirely. Even if it initially had a dense gas envelope and oceans, the stellar wind and flares could have simply blown them into space. First, light hydrogen would escape, then oxygen and nitrogen. Ultraviolet radiation would break down water molecules in the atmosphere into hydrogen and oxygen, and they would also be carried away. As a result, a dry, airless ball, similar to our Mercury or the Moon, might remain from a once potentially habitable world. Let's briefly deviate from flares and look at other problems. As we already mentioned, tidal locking. Being so close to the star, the planet is almost certainly in synchronous rotation. This creates an extreme climate. On the day side, which eternally faces the star, the temperature can reach the boiling point of water, even despite the dimness of the star. And on the night side, immersed in eternal darkness, there would be a cold comparable to Antarctic, where atmospheric gases could freeze out and precipitate onto the surface as snow. Theoretically, a dense atmosphere could redistribute heat from the day side to the night side with strong winds, smoothing out temperature differences. But we have just established that preserving a dense atmosphere under such conditions is an almost impossible task. So, most likely, we are dealing with a world of sharp contrasts, a scorching hell on one hemisphere and an icy desert on the other. A narrow terminator zone, where moderate temperatures could exist, would be a zone of eternal hurricane winds blowing from the hot day side to the cold night side. And there is another less obvious, but no less important factor: the history of the planet's formation itself. Proxima b is located very close to its star, inside the so-called snow line. This is an imaginary boundary in the protoplanetary disk, beyond which volatile compounds, such as water, can condense into ice. Planets forming inside this line are typically born dry and rocky. It is believed that water was delivered to Earth later, during bombardment by asteroids and comets from the outer, colder regions of the solar system. Did something similar happen in the Proxima Centauri system? We don't know. Perhaps Proxima b was initially a dry world, and it never had significant water reserves that could form oceans. In this case, the question of habitability is irrelevant. Putting all these factors together, lethal radiation, constant atmospheric erosion, extreme climate due to tidal locking, and probable initial dryness, we get a rather bleak picture. Proxima b is a prime example of why formal placement in the habitable zone guarantees nothing. It is in the right place, but at a very bad time, and around a very unsuitable star. This does not mean that it should be written off completely. The universe loves to surprise. Perhaps Proxima b has a very strong magnetic field. Perhaps it initially had such a dense atmosphere that even after billions of years of erosion, something remained of it. Perhaps life exists deep beneath the surface, protected from radiation. But if we talk about probabilities based on our current knowledge, the chances of finding an Earth-like world on Proxima b are extremely small. This discovery became an important lesson for the entire exoplanet hunting community. It forced a reassessment of habitability criteria and a closer look at the nature of the parent star. Red dwarfs, which once seemed the best hope for finding life, are now viewed with great skepticism. Perhaps the true cradles of life should be sought not around the most numerous and long-lived stars, but around quieter and more stable ones, like our Sun. The story of Proxima b is a story of dashed hopes, but that does not make it any less interesting. On the contrary, it has become an ideal natural laboratory for studying how planets survive or do not survive in extreme conditions. And, as it turned out, the story of this system does not end with one, albeit such a famous planet. Further observations showed that Proxima b is not alone in its misfortune. It has other sisters. The discovery of Proxima b in 2016 was a triumph of the radial velocity method and forever changed our perception of the nearest stellar neighborhood. But science never stands still. One discovery gives rise to new questions and stimulates further, even more precise observations. Was Proxima b a solitary planet, miraculously surviving in orbit around a turbulent star, or was it just the first detected member of an entire planetary family? To answer this question, astronomers continued to carefully listen to the Doppler whisper of Proxima Centauri, hoping to catch signals from other, still invisible worlds. This work required even more patience and skill. The signal from Proxima b is bright, and it could be subtracted from the overall data. Now scientists had to search the remaining noise for even weaker and possibly longer periodic oscillations that could indicate the presence of other planets, either smaller in mass or in more distant orbits, and their persistence was rewarded. In 2019, an international group of astronomers led by Mario Damas from the Italian National Institute for Astrophysics, analyzing data collected over 17 years using the HARPS and UVES spectrographs, noticed something intriguing. In addition to the already known 11-day signal from Proxima b, another very weak and very long cycle was traced in the data. The star seemed to perform another oscillation with a period of about 1,907 days, or approximately 5.2 Earth years. The signal was at the very limit of detectability, and the researchers treated it with great caution. Its amplitude was even smaller than that of the signal from Proxima b. It could have been caused by other reasons, such as long-term magnetic activity cycles of the star itself. Independent data were needed to confirm or refute the existence of a second planet. And here another method came to the rescue. Astrometry. Astrometry is the oldest field of astronomy, which deals with the super-precise measurement of positions and movements of celestial bodies. If the radial velocity method measures the star's movement towards and away from us, then astrometry measures its tiny displacements on the celestial sphere. When a planet orbits a star, it causes the star to describe a tiny ellipse in the sky. Seeing this displacement is incredibly difficult, but the Gaia Space Telescope of the European Space Agency was created precisely for such tasks. A team of astronomers turned to Gaia data, as well as archival images taken by the Space Telescope over many years. And although this data was also not definitive, it showed that there is indeed a perturbation in the motion of Proxima Centauri that is well consistent with the presence of a second, more massive and distant planet. In January 2020, the team officially announced the discovery of a candidate planet, named Proxima Centauri c. It was a completely different world, unlike its inner neighbor. According to the data, Proxima c is a so-called super-Earth, or possibly a mini-Neptune. Its minimum mass is estimated at approximately 7 Earth masses. It orbits at a much greater distance from its star, about 1.5 astronomical units. This is 1.5 times farther than Earth is from the Sun. At such a distance from a dim red dwarf, the conditions are completely different. Proxima c is far beyond the habitable zone. It receives only about 3 to 4% of the heat from its star that Earth receives from the Sun. It is a cold, icy world. The equilibrium temperature on its surface, without considering a possible greenhouse effect, is about -234 degrees Celsius. It is colder than on the surface of Pluto. The nature of this planet remains a mystery. With a mass of 7 Earths, it is on the border between rocky super-Earths and gas mini-Neptunes. It could be either a large rocky planet with a very dense atmosphere, or, more likely, a world rich in ices and volatiles, with a thick gas envelope of hydrogen and helium, similar to Neptune or Uranus in our solar system. But the most surprising thing about the story of Proxima c is that in 2020, astronomers may have been able to see it. A group of researchers, working with the sphere spectrograph on the Very Large Telescope in Chile, obtained a direct image of a faint light source near Proxima Centauri, whose position coincided with the predicted orbit of Proxima c. If this image is definitively confirmed, it will be a real breakthrough. Proxima c could be the closest exoplanet to us that has been directly photographed. This would allow its light to be studied and the first data on its atmospheric composition to be obtained. But the story did not end there. Astronomers continued to analyze the data from the HARP spectrograph using even more advanced processing methods. In 2022, another team, led by João Faria from the Institute of Astrophysics and Space Sciences in Portugal, announced the discovery of a third signal. It was even weaker than the previous two. This signal indicated the presence of a third planet, even closer to the star than Proxima b. This planet, named Proxima Centauri d, turned out to be a real dwarf. Its minimum mass is only about 1/4 of Earth's mass, 0.26 to be precise. It is one of the lightest exoplanets ever discovered by the radial velocity method. It is lighter than Mars, which weighs about half of Earth. Proxima d orbits very close to the star, completing one revolution around the star in just 5.12 Earth days. It is even closer to the fiery dragon than Proxima b, and, consequently, receives even more radiation. There can be no talk of any habitability here. Most likely it is a scorched, atmosphereless rocky ball. But its very existence is an amazing fact. It shows that even the smallest and dimmest stars can form entire planetary systems and with very diverse architectures. Let's now look at this family as a whole. We see an amazing, compact structure, completely unlike our solar system. In the very center, almost touching the star, orbits the tiny, scorched world of Proxima d. A little further, in the formal habitable zone, but under constant bombardment by flares, is Proxima b, an Earth-sized world with a tragic fate. And far outside in the icy darkness orbits the cold giant Proxima c. This system poses many questions for planet formation theorists. How could such different planets form and remain in their orbits around such a small star? The origin of Proxima c is particularly interesting. At such a great distance from the star, the protoplanetary disk must have been very sparse, and it would have been very difficult to form a planet with a mass of 7 Earths there. One hypothesis suggests that it formed much closer to the star, beyond the snowline, and then migrated to its current distant orbit. Studying this triple system is key to understanding planet formation processes around the most common type of stars in the galaxy. Each of these planets, Proxima b and c, is a unique case for study. They represent 3 completely different worlds formed under different conditions, but around the same, very difficult star. Thus, our invisible neighbor turned out to be not just a solitary star. It is an entire system, miniature and strange, full of mysteries and paradoxes. It is no longer just a point on the map. It is an entire family of worlds, each with its own story. And to unravel these stories, to understand what these planets are made of, whether they have an atmosphere, and what their actual conditions are, we need ever more sophisticated tools and methods. We need to learn not just to hear the whisper of the star, but to decipher it in the smallest detail. Our journey to Proxima Centauri has so far been a journey of ideas and discoveries. We have talked about what we know about the nature of the star, its character, and the planets orbiting it. But now let's pause for a moment and ask ourselves, how do scientists obtain all this astonishingly detailed information about an object that is just a tiny point of light, even in a powerful telescope? The answer to this question is a story of human ingenuity, of the creation of incredibly precise instruments, and of the development of ingenious analysis methods that allow us to turn dim starlight into a treasure trove of knowledge. This is real interstellar detective work. The central tool in this work, as in all modern astrophysics, is spectroscopy. The idea behind this method is simple, but its capabilities are practically limitless. When light from a star passes through a prism or diffraction grating, it is broken down into a spectrum, the rainbow we are familiar with from school. But if you look at this spectrum very carefully, with precise instruments, you will see that it is not continuous. It is dotted with dark vertical lines. These are so-called absorption lines. Their nature was deciphered in the 19th century. Each chemical element in its gaseous state can absorb light at strictly defined wavelengths unique to it. When light from the hot depths of a star passes through its cooler outer atmosphere, atoms of various elements, hydrogen, helium, iron, calcium, and others, absorb their characteristic portions of light. As a result, the spectrum that reaches us develops gaps, dark lines. This is a kind of fingerprint of chemical elements. By analyzing the position and intensity of these lines, we can accurately determine what the atmosphere of a star, located light years away from us, is made of. It is thanks to spectroscopy that we know that Proxima Centauri, like the Sun, consists mainly of hydrogen and helium, but also contains a small amount of heavier elements. But this is only the beginning. The spectrum carries much more information. The width of these absorption lines can tell us about the temperature and pressure in a star's atmosphere. And their shift, that very Doppler effect we have already discussed, is key to finding exoplanets. When a star moves towards us, all its spectral lines shift to the blue end of the spectrum. When it moves away, they shift to the red. By measuring these tiny shifts with high-precision spectrographs, such as HARPS or its successor Espresso on the Very Large Telescope, astronomers were able to detect all 3 planets in the Proxima Centauri system. The precision of these instruments is such that they must be isolated in vacuum chambers with stable temperatures, so that the slightest fluctuations of the Earth's atmosphere or the thermal expansion of the instrument's parts do not distort the results. Essentially, these are the most sophisticated and stable thermometers and rulers ever created by humankind. Spectroscopy also allows us to study a star's magnetic field. A strong magnetic field causes the so-called Zeeman effect, splitting a spectral line into several closely spaced components. By measuring this splitting, we can map the magnetic fields on the surface of Proxima Centauri, determine the location and strength of its giant star spots, and better understand the mechanism of its violent flares. The second most important method is photometry. This is, at first glance, a simpler task, accurately measuring the brightness of a star over time. Scientists construct a so-called light curve, a graph showing how an object's brightness changes. It was photometry that first allowed the discovery of Proxima's flaring nature. On its light curve, its flares appear as sharp, giant peaks. By observing the star over many nights, astronomers can gather statistics on these flares, how often they occur, what their power is, how quickly they ignite and fade. This data is critically important for assessing the conditions on its planets. Photometry is also the basis of another popular method for finding exoplanets, the transit method. If a planet's orbit is aligned such that, from our perspective, it passes directly in front of its star's disk, then during this passage, or transit, it will block a tiny portion of the star's light. On the light curve, this will appear as a small, periodically repeating dip. It was with this method that the Kepler Space Telescope discovered thousands of exoplanets. In the case of Proxima b, scientists searched for such transits for a long time and persistently. After all, if they had been detected, it would have allowed for an accurate measurement of the planet's radius, and knowing its mass from the radial velocity method, its density could have been calculated, unequivocally stating whether it was rocky or not. Unfortunately, numerous searches, including those using the TESS Space Telescope, have so far been unsuccessful. This means that Proxima b's orbit is most likely slightly inclined with respect to our line of sight, and transits do not occur. But modern astronomy is no longer limited to the optical range. To get a complete picture, it is necessary to observe Proxima Centauri across all ranges of the electromagnetic spectrum. And here, radio telescopes play a key role. Observations in the millimeter and submillimeter waves are particularly important, which are carried out by the Atacama Large Millimeter Submillimeter Array, ALMA, of radio telescopes, located on the high-altitude plateau in the Chilean Atacama Desert. ALMA is not a single telescope, but a giant interferometer consisting of 66 antennas that can work as a single unit, simulating a telescope with a diameter of up to 16 kilometers. Such a system has incredible resolving power. It was ALMA in 2017 that made an astonishing discovery. Observing Proxima Centauri, scientists detected a faint glow around it emanating from cold dust. This glow formed a structure resembling an extended belt. This discovery was extremely important. It hinted that Proxima Centauri's planetary system might be much more complex and richer than we thought. This dust belt could be an analog of our Kuiper belt, a region beyond Neptune's orbit populated by icy bodies. Moreover, ALMA's data indicated the possible existence of a second, even colder and more distant dust belt, as well as a gap between them that could have been cleared by the gravity of another, as yet undiscovered, massive planet, a kind of super-Earth or Neptune. This turns the Proxima Centauri system into a miniature copy of our solar system, with its rocky planets in the inner part and with analogues of the asteroid belt and Kuiper belt in the outer part. Studying these dust structures gives us invaluable information about how this system formed and evolved. Finally, we cannot fail to mention space telescopes operating in high-energy ranges, such as Chandra for X-rays and those for ultraviolet wavelengths. It is they that allow us to study the most violent manifestations of Proxima's character, its flares and corona. Hubble was able to capture that record-breaking ultraviolet flare, and Chandra constantly monitors the star's X-ray radiation, which is the best indicator of its magnetic activity. Thus, our knowledge of Proxima Centauri is the result of a complex synthesis of data obtained by many different instruments, operating in different parts of the planet and in space, and observing in the most diverse ranges of the electromagnetic spectrum. It is a gigantic scientific cooperation where spectrographs listen to the star's breath, photometers track its pulse, and radio telescopes see the skeleton of its planetary system. Each new observation, each new method adds another piece to this complex mosaic. And this mosaic tells us a story that not only satisfies our curiosity, but also inspires the next boldest step, to try one day to go there and see everything with our own eyes. Our study of Proxima Centauri has so far been a journey of light. We have analyzed photons that have traveled 4.2 light-years to bring us news about the nearest star system. We have learned to decipher these messages, extracting information about the mass, temperature, chemical composition of the star, and even the existence of planets orbiting it. But deep down, every researcher, every person looking at the stars, harbors a dream. A dream not just to observe from afar, but to go there, to cross the interstellar void, and to see it all with their own eyes. Proxima Centauri, being our closest neighbor, automatically becomes the main and most obvious target for humanity's first interstellar flight. But this very phrase, interstellar flight, sounds like science fiction, and for good reason. The distances in space are so vast that our minds can hardly grasp them. Let's try to imagine it. The distance to Proxima Centauri is about 40 trillion kilometers. The fastest object ever created by humans is the Parker Solar Probe. At its closest approach to the Sun, it accelerates to a speed of about 192 kilometers per second. Even if we could launch a spacecraft at this incredible speed directly towards Proxima Centauri, the journey would take about 6,600 years. 6,600 years. That is more than all of recorded human history, from ancient Sumerians to the present day. Obviously, traditional rocket technologies, based on chemical fuel, are completely unsuitable for interstellar travel. Fundamentally, new ideas and technologies are needed that would allow us to reach speeds that are a significant fraction of the speed of light. And one of the most promising and, at the same time, most ambitious of these ideas was formulated within the framework of a project that sounds as if it came straight out of a science fiction novel. This project is called Breakthrough Starshot. On April 12, 2016, on the 55th anniversary of Yuri Gagarin's flight into space, investor and philanthropist Yuri Milner and legendary theoretical physicist Stephen Hawking announced the launch of this research and engineering program with a budget of $100 million. The program's goal is to prove the viability of the concept of ultra-fast unmanned flight to Alpha Centauri. The project is based on an idea that has been around for a long time but has never before been considered with such seriousness and funding. It is the concept of a light or laser sail. Imagine a tiny spacecraft, a nanocraft, no larger than a postage stamp. Its mass is only about 1 gram. On this miniature chip, called a star chip or stellar chip, are all the necessary systems: a camera, sensors, navigation instruments, and a laser transmitter for communication with Earth. This nanocraft is attached to an ultra-thin and ultra-light sail, several meters in diameter. The material of this sail must be incredibly strong, lightweight, and highly reflective. And now, the most important part: the engine. The engine in this system remains on Earth, or rather, in Earth's orbit. It is a giant phased array of thousands of powerful lasers that can focus their light into a single, incredibly powerful beam with a power of up to 100 gigawatts. For comparison, this is comparable to the power consumed by an entire country. And here's how it's supposed to work. A fleet of thousands of such nanocrafts is launched into orbit. Then, the giant laser installation is aimed at the sail of one of them. The most powerful beam of light strikes the sail. Light, as we know from physics, consists of photons, which, despite having no rest mass, possess momentum. Each photon, reflecting off the mirror surface of the sail, transfers a tiny fraction of its momentum to it. This is light pressure. At normal light intensity, it is negligible, but when a beam with a power of 100 gigawatts hits the sail, this pressure becomes colossal. According to calculations, this laser strike should accelerate a 1-gram nanocraft to a speed of about 60,000 kilometers per second. That is 20% of the speed of light. 20%. At this speed, the journey to the Alpha Centauri system would take not 1,000 years, but only about 20 years. And a signal sent from this spacecraft would return to Earth in another 4 years. That is, within a single generation, we could launch a mission and receive results from it. Of course, the technological challenges facing the implementation of this project are colossal. Each one is a task at the limit or beyond current capabilities. Firstly, the laser itself. Creating and synchronizing a phased array with a power of 100 gigawatts, capable of keeping the beam focused on an object a few meters in size, at a distance of millions of kilometers. This is a task of incredible complexity. Secondly, the sail. It must be made of a material that can withstand the colossal energy of the laser beam and not melt or vaporize. It must be almost perfectly smooth and reflective, so as not to absorb energy and lose stability. Various nanomaterials, such as graphene or dielectric metamaterials, are currently being considered. Thirdly, the star chip itself. Fitting all the necessary instruments onto a 1-gram crystal and making them resistant to years of cosmic radiation is a huge problem for microelectronics. Fourthly, navigation and communication. How to control a spacecraft traveling at such a speed, how to correct its course, and most importantly, how to receive data from it. The signal from its tiny laser transmitter, after traveling 40 trillion kilometers, will be unimaginably weak. To receive it, a receiving system comparable in power to the one that launched it will be needed. And finally, the problem of braking. In the basic concept of the project, deceleration at the target is not provided for. The nanocraft will fly through the Alpha Centauri system at a speed of 20% of the speed of light. All scientific work, photographing planets, collecting data, must be performed during the few hours it will be flying past. It's like trying to photograph a bullet by shooting it with another bullet. Despite all these difficulties, the Breakthrough Starshot project is not just a fantasy. It is a serious scientific program on which the world's leading physicists, engineers, and astronomers are working. It stimulates the development of a whole range of breakthrough technologies in the fields of lasers, nanomaterials, and microelectronics, which will find applications in other areas as well. Proxima Centauri and its planets are the main target of this hypothetical mission. Imagine, 20 years after launch, a tiny spacecraft flies past Proxima b. Its camera takes a series of pictures, and then, another 4 years later, we on Earth receive the first close-up image of another world in history. We will be able to see if it has continents and oceans and clouds in its atmosphere, or if it is just a barren rocky ball. We will be able to distinguish land from water, measure the temperature on the day and night sides. This single photograph will answer more questions than all our telescopic observations over 100 years. It will turn an abstract data point into a real, tangible place. Proxima Centauri will cease to be just an invisible star. It will become humanity's first step beyond its cradle, the first destination on our long journey to the stars. And even if this first step is taken by a tiny 1-gram robot, it will be a giant leap for all of humanity. We began our journey with one simple and almost childlike question. Why can't we see the star closest to us? This question, like a thread, has led to a whole series of discoveries, each more complex and amazing than the last. We have moved from a simple realization of dimness to understanding the most complex processes in stellar interiors. We have seen how a star's mass determines its fate, turning some into bright but short-lived luminaries, and others into modest but almost eternal long-livers. We have realized that our human vision is only a narrow window into reality, and that in the infrared light invisible to us, our quiet neighbor shines like a bright beacon. We have uncovered its main alarming secret. Behind the facade of calmness lies a furious and violent nature capable of incinerating any nearby world. We have witnessed the discovery of an entire planetary family around this fiery dragon, a family that includes a scorched dwarf, an Earth-sized world with a tragic fate, and a distant icy giant. We have seen what sophisticated instruments and methods humanity has created to hear this quiet stellar whisper across the abyss of space. And finally, we have peered into the future and seen a bold dream, a project of interstellar flight that could one day turn this distant point into a real destination. What other secrets does this quiet neighbor hide? Are there more planets there? Are there icy moons like Europa or Enceladus with subsurface oceans around Proxima Centauri? The answers to these questions await us in the future. M.